So good afternoon, ladies and gentlemen. Welcome on next webinar related to release of version 22.1. And today's topic is actually what's new in concrete in this version. My name is Tomáš Pajl and I will be today's presenter. As always, you are muted during the webinar, but feel free to ask the questions in the dedicated panel of GoToWebinar, because today with me is my colleague Paolo Valach, who will be answering your questions. And if some question will not be answered during the webinar, definitely we will reach you via email later on. And also this webinar will be available on our YouTube channel. What's today's agenda? We will touch the column design with extended second order calculation option. Then we also revise how the axial force on ribs is recalculated to additional bending moment. Also, we added new option to apply minimum reinforcement onto the slabs. And also we extended bill of material to include the 2D reinforcement manually added. So it means user-defined reinforcement. So let's get started. Column design and second order. Actually, we extended this functionality in terms of to provide more design options. So there is brand new method which is mentioned in the Eurocode, the nominal stiffness method, which you can use as an alternative method to calculate second order moment. To consider the low duration, you are now able to input user-defined ratio between quasi-permanent and design moment to actually determine the effective creep coefficient. And last small thing, but can be also interesting, is automated neglecting of creep effect when code-based conditions are fulfilled. So let me a little bit dive in. Nominal stiffness method, as I said, it's alternative method to calculate second order moment. It's based on assumption that the nominal stiffness is evaluated considering the effects of creep and cracking via the coefficient Kc, and also the reinforcement via the second part of the equation. And this nominal stiffness is actually used to calculate the buckling load. And this buckling load is then used to compare the value with the axial load and multiply actually the first order moment by this part. Yeah. So basically related to the SCIA Engineer, in the concrete settings, I mean global settings, or even on the level of concrete member data for individual members, you can now choose whether you would like to select nominal curvature method as an original solution, now the nominal stiffness method, or you can, for instance, not consider second order effect at all. So it's first point. The live demo will follow, so just be patient, because I would like to little bit also mention the user-defined ratio for determination of effective creep coefficient. The effective creep coefficient is actually used in both methods, simplified methods, so curvature method or stiffness method. Basically, it would be great to have this ratio between quasi-permanent model moment and design moment automatically evaluated, but it's not so easy. So at least we now allow to input this ratio manually. So again, in the concrete settings in chapter internal forces, you can input this coefficient globally, but it's also available locally via concrete member data. And last, here you can see the paragraph from the Eurocode where are mentioned the conditions when the neglecting of creep effect you may apply. And actually these conditions automatically checked, and when they are satisfied, automatically we set the effective creep coefficient as a 0. So despite the fact that you will input, for instance, here 0.7, if those conditions are fulfilled, then the effective creep is completely neglected. Of course, you can always neglect the creep, just put this coefficient as a 0. Okay, and to provide you a viewpoint how it works in SCIA Engineer, I prepared small example, but not just to demonstrate the functionality itself, but also a little bit discuss which method you can or should be chosen, because actually we have 3 methods in Eurocode mentioned: nominal stiffness and nominal curvature as a simplified approach, and general method, which is based actually on the full nonlinear analysis material as well as the geometrical. And maybe information for you that this option for 1D elements will be available in very next version in 64-bit together with existing solution for 2D. So you can looking forward for this option as well. But today we will just compare nominal stiffness and nominal curvature method. Here you can see that the numerical study will focus on changing of the cross section and also changing of the reinforcement ratio. And yeah, because this model is undetermined, it means that always the applied load is a little bit different, but the internal forces and first order moments and axial load will be for all options the same. And to be able to simply change the reinforcement, we just use same number of bars, but with different diameter. And of course, we will look a little bit about the effect of effective creep. So originally 1.0, but here there will be option also to decrease the effective creep to lower level. Okay, so now I will switch to SCIA Engineer. Here is the simple model, and it's one of the options. If I select the member in the concrete member data, you can check what type of method is used. So now we are considering for second order eccentricity the nominal curvature method, and the coefficient for effective creep of the moments is 1.0. And because I have already applied some user reinforcement, I can go and display first maybe just the normal force to see that it's really the axial load is what was mentioned on the slide. And sorry, I just focus on selected member. So first the axial load and first order bending moment. Now if we check the increase of the bending moment due to the second order, you see that maybe I will change the visualization a little bit. You can see that there is the increase for the curvature method about 90 kilonewton meter. Now what I can do is just simply go back to the concrete member data and change this method to the nominal stiffness, but still with the same effective creep coefficient. And you will see that the results will be different. And from 150 kilonewtons meter, we are now just slightly above 200 kilonewton meter. So you can see that in this case, actually the method based on nominal stiffness is or gives a smaller design bending moment. To explore this effect, we will then show the study. But before that, just last option, which is new, again via concrete member data or globally, we can change also the ratio of bending moments on quasi-Pennon level and design level. And again, just refresh the results to see the effect of this option. Yeah. And this effect will not be so significant like the change of the method, but you can see that in case of 205, now we have 201. Yeah. Now what we can do actually is just show you the study. So now we can play with that we can, for instance, decrease the amount of the reinforcement. So now I will select just those columns which we are interested in. So same load. And again, just if you want to check before the analysis what the assumption is for all the columns, quickly you are able to see the concrete member data, and you can see that now I have mixed option. So for instance, I again can start with the nominal curvature and with, for instance, coefficient of moment 0.7 and display the results. And we will see what is the impact. I will display the results on member. And you can see that actually for method of nominal curvature, doesn't matter whether you increase the reinforcement or decrease the design moment, is actually the same. While if we now change the assumption, you will see the significant difference. So just simply change the method and recalculate now project with this option of nominal stiffness method. You will see that the effect of reinforcement increase or decrease influence the results quite significantly. Yeah. Just now it's not obvious. Something is wrong. So maybe I will try to open the project again. But actually we can see the impact in this table where we have nominal stiffness method and nominal curvature method. And you can see that we have curvature method and the reinforcement ratio is increasing and we have still the same design moment, while in case of stiffness method, actually with increasing of the reinforcement, we decreasing the design bending moment. So actually the moment from the second order. Yeah. So just let me check the results correct. And meanwhile, there is also another very interesting effect, because if you can see also the changing of the cross-section has different behavior for nominal stiffness method and nominal curvature, because when we decrease the cross-section area, actually the bending moment from the curvature method is increasing. And you can see that with small cross-section, then the effect is smaller and smaller, while for the curvature method, actually the situation is opposite. We increasing the cross-section and actually the design bending moment is bigger. Yeah? And then we have here some really huge bending design moment, which we will explore a little bit later. Yeah? So just to prove, I hope what I would like to show you is concrete member data, nominal stiffness method. Yeah, we will leave the coefficient as it is. Okay, just current. And scale the results. And here you can see the effect which I would like to show you. Yeah? So for the nominal stiffness method, just increasing the amount of the reinforcement, and you can see that we have significantly different design bending moments here. And now if I change the member data to select nominal curvature method and once more display the results, you should see still the same value. Yeah? Okay, so what does it mean? For curiosity, we also checked the capacity check. So of course, using the reinforcement and second order moment or total design moment, then you can go to the capacity check and check also the results in terms of, and again, on all members. So I will just select the current one because else is not the reinforcement. So we can get the capacity values. And it's interesting to see that for both methods, if we have, for instance, cross-section 400 to 400, the results are somehow corresponding. You can see that nominal stiffness method is very conservative, and mainly it's not usable when the applied axial load is very close or even bigger than the nominal buckling load. So that's the reason why here is such big value, because if the axial force is, maybe I will show it in this slide. If the axial load is bigger than the buckling load, then we multiply automatically first order moment by coefficient 100. And even if the ratio is a little bit below the 1, but very close to 1, then the design bending moment is really big. On the other hand, you see that actually for the opposite case, where we have big cross-section, which is highly reinforced, then the stiffness method is maybe better option, and in this case the curvature method is much more conservative. So what we will do with together with release of next version, then definitely we will compare also those two simplified methods with general method to see actually what can be used, because of course simplified methods are more conservative than this general one, but maybe we can find out some recommendations when each of those methods can be used. But for sure, at least from the Eurocode point of view, nominal curvature method should be used just for symmetrical cross sections, which are also symmetrically reinforced, while, for instance, nominal stiffness method should be used much more general, but also with some limitations like cracking or considering cracking of adjacent members, etc. So it's first topic, and here you can see what I just wanted to highlight, that doesn't matter of what reinforcement ratio, what you will use for curvature method, you will get almost same design bending moment, while nominal stiffness method gives very different results for each reinforcement ratio. And if the axial load is very close or bigger than buckling load, nominal buckling load, then of course you cannot use this method at all. So it was first topic. Second topic is recalculation of the normal force on ribs, where the goal was to provide much more accurate results for cases like areas near supports, where actually originally we just increase the bending moment for areas where it was positive bending moment. So now it's based on not just axial load, which is tensile, but you will see later that we now recalculate the internal force or normal or axial force to additional bending moment for any axial force on the rib. Also, it will solve the issues which we had in case rib was oriented above slab, because then of course we have tensile axial force above the support, but originally in this area the bending moment was not increased at all, because originally we focused on the bending moment sign and not the axial force sign. And also you will see that we had a bug there related to the consideration of the different effective widths used for integration of forces and for actual rib design, because actually the recalculation of the axial force should be based on the cross section from the effective width for integration of forces and not from the width which is used to define the cross-section for the design. And minor improvement, but for transparency also important, is that now we visualize actually both effective widths. So here on the figure you can see that actually we have effective width which is same, but design cross-section is in both cases different. And now we visualize the cross-section shape from the effective width which is used for concrete rib design, while the integration width is presented as you can see, yeah. So by this gray strip. So again, I will jump. Maybe I will close this file first and display example related to the rib axial force topic. First, just introduction of the project. You can see that I have two continuous ribs and one solution which is used as a reference, just simply T-beam. It's applied same load on both, and it's important that the first continuous beam differs from the another just using different cross-section for the design. So effective width for integration of forces is the same for both, but the cross-section for the design is here the T-section, which is even bigger than the integration width, just for the purpose of this example, because it's actually nonsense. And here we have just rectangle, so actually the effective width for cross-section is smaller than the effective width for integration of forces. Yeah. And again, we can just display, maybe just to check before we will calculate or display the results. I will show you where you can activate the option. So if you want to have this option, you first select the user type of load input or internal forces component selection. Then you need to switch off the axial force, but after that you need to check that you want to recalculate the axial force to additional bending moment. Yeah. Okay, and finally we can display the results of directly bending moments. And since the T continuous beam is our reference solution, you can see that we have a lot of differences. Yeah? So it's results from the original version of version 22. And you can see that the positive bending moment is not achieved like on the reference beam. And the reason is, as I indicated, that actually for the eccentricity of the axial force, we took the effective width from the cross-section and not from the width for integration of forces. So that's the reason why here we have bigger value, because effective width is smaller, and here we have a smaller value because effective width is bigger than for integration of forces. So it's first topic. Second topic is, maybe I will display now for second the axial force. And here you can see that in this area we have tension, and here we have compression. Yeah? So if I go back to the bending moment, here you can see that for axial force which is in tension, some increase of the moment is correctly the additional bending moment is correctly calculated, while for the area where is axial or where was axial force in compression, actually there is no increase of the additional moment. So original estimation or configuration was that, okay, for compression axial force, we will not recalculate the additional bending moment because for the design of the rib part below the slab, it has no influence because it influences the amount of the reinforcement in the slab. Later on, we will see that it's not fully correct if we have rotated cross-section. And maybe, yeah, so you can see that actually here I have bigger value than for the rib model. Yeah. Maybe now I will show you also results in model which is completely same, just we have rotated the rib above the slab. And again, we have some reference solution as a T-beam, and we have solution for the ribs or via ribs. And if we display, maybe I will just isolate or focus on this. If we display the results, you will see that here the situation is even worse. So let's start first with the axial force. Here you can see that now we have tensile axial force above support, while in the middle of the span we have actually the compression. And if we go back to the bending moment, you can see that the increase of the bending moment above support is not done at all. And what's worse, that actually the bending moment in the middle of the span actually it's decreasing from the reference value, because actually we consider the compression force. So actually we decrease the total design bending moment. Yeah. So for this use case, actually the recalculation of the axial force was not useful at all. Yeah. And now I will just recalculate the project, and we will calculate the design bending moment with recalculation of the axial force in the version 22.1. And you should see the significant difference. And yeah, maybe I will just display first just the final moment, and you can see that now the moments, the above support as well as the positive bending moments are almost same, like on the reference example, and not just for the ribs below the slab, but also for the cases where we have ribs above the slab. Yeah. It's important that, as I said, now the recalculation is done for any axial load, so it doesn't matter whether positive or negative, just to have transparent results in terms of where you compare the results, for instance, with this simplified T-beam, because of course then it can be discussion whether increasing of the moment above the support, for instance, in this case, is necessary or not. But to have really fully transparent solution, we decided to make it in this way. Yeah. And to see that it's really done across whole beam, you can see that also in this case we are increasing the bending moment by this neglecting of axial load. Okay, it's the topic of recalculation of normal force on ribs. Of course, always you can, for instance, design reinforcement including the axial force if necessary, and there was presented or posted on YouTube channel some webinar related to the rib design. So there is explained what are all the options you can do related to the ribs. But now we need to go to additional topic, now related to the 2D slab design, because based on your feedback, we implemented very small feature, but with quite significant impact, and this is the application of minimum reinforcement, because originally it was possible just to apply this reinforcement in tangent area only, while now you have second option to apply this minimum reinforcement in the design on the whole member. This option is specifically for slabs, so the member type must be the plate. But if, for instance, you have walls with out-of-plane bending, it's possible to use this functionality, but unfortunately, you have first to change the member type to plate, and then all the detailing rules, including the minimum reinforcement, are applied based on rules. But actually, such option is directly mentioned also in the Eurocode, so it's actually maybe obvious. And as a consequence, then you can completely design the reinforcement just using the additional bars in the design template, because since the reinforcement is on whole member, at least the minimum one, then the provided reinforcement is also designed everywhere, and the option basic reinforcement, of course, you can use it to manually input what's your preference, but if you want, for instance, basic reinforcement to be designed automatically, you just can play with the additional bars. So we will now jump to the live demo, and so I have some simple slab, and if you want to play with the minimum reinforcement, you can of course do it in global setup, where if I just focus on the plate, you have option to apply some minimum reinforcement. You can say whether you would like to use the automated option, which then the minimum reinforcement is calculated based on code, or you can define the reinforcement also by your user preference, and you can change the minimum reinforcement differently for upper and lower surface. And here there is new option to actually apply the reinforcement not just in the tangent area but on whole member. And of course, the automated calculated minimum reinforcement or user-defined value will be used. Okay. But of course, you have this option, and it's not of course because it's only one option from the detailing part, which is possible to change in the concrete member data. So in concrete member data, you can choose this option also on the member level. So specifically member from member, you can choose whether you want intention area or only or whole member. So now we have intention area only, so original solution. So I just select the command for the reinforcement design and display the results. For instance, for the lower surface in direction 1, you can see that actually we have areas where the reinforcement is 0. And we can see the difference of application minimum reinforcement if we select require static reinforcement, because it's without this detailing rules. So if I now display the results, you can see that the area of the reinforcement which is designed is smaller, because now we are focusing only on the reinforcement which is required by the ultimate limit state. And now what I can do is actually to go to the concrete member data and change the option to apply the minimum reinforcement on whole member. So results are deleted, and I can go back to the command. Now here it is. So same situation. Now I will stay with the statically required reinforcement, which should not be changed at all. Yeah. So still you are able, even if you select the minimum reinforcement on whole member, you can see where actually you need reinforcement just based on the ultimate limit state or even the serviceability limit state. But then we can go to the required reinforcement, including this minimum amount of reinforcement. And now you can see that I have different visualization because now my minimum reinforcement is not 0 actually, but or the value of reinforcement is not 0, but the application of minimum reinforcement is everywhere. So we have this amount here. And then I, for instance, can go and design the provided reinforcement. So I go to the design defaults, apply the provided reinforcement template, and I can modify the content. And you can see that, for instance, I have basic reinforcement switched off here. And for instance, I can say that I would like to see results for list of diameter, and I will select diameter 8, 12, 16 with spacing 150. Yeah? So I will copy this option for all directions for upper and lower surface, and just go to the provided reinforcement. Yeah, for instance, again, the direction 1 lower surface. Now, not just required reinforcement will be designed, but also the provided reinforcement. Of course, you can do it at once, but for this purpose, it's splitted. And you should be able to see the basic reinforcement actually automatically designed. Yeah. So here you can see that diameter 8 and spacing 150 is my basic reinforcement. Yeah. Of course, now I can a little bit play with that. So I can try, for instance, diameter 6 as well, just for curiosity. And refresh the results. And we will see whether basic reinforcement can be, for instance, in some cases, diameter 6. Yeah. So let's check it. And you can see that still I need diameter 8, 150. Maybe we can prove. So I can select as prof, or maybe I can change or check it. So it's 335, the area, and what is required actually as a minimum. If I go back to the required, it's 330. Yeah? So the results are as expected. Maybe last point to this, we got feedback that actually it would be great to combine more diameters and more spacing options. And if now we have also the minimum reinforcement applied everywhere, then it makes big sense. So in some next version or very next version, you can expect also extension in this direction. So then actually the application of provided reinforcement can be done really from the list of specific options of diameter and spacing. to really have the provided reinforcement as you wish or as what you often applied. And last topic which I would like to show you today is the bill of material including to the reinforcement. So basically, if now I select, for instance, provide reinforcement or even the required, I would like to display just the summary table where, for instance, maybe I will select the provided, it will be better. So you will see, for instance, the amount of the reinforcement in terms of weight of the reinforcement per unit volume of concrete, but it's still just not using the user-defined reinforcement. Of course, you can apply the user-defined reinforcement, and if you do that, then you can get, for instance, the bill of material much more precise using really the geometry of meshes. So it was possible just for 1D, but from version 22.1, it's now possible also for 2D. So just I've already applied some reinforcement on the lower surface. So it means user reinforcement. And if there is user reinforcement, you can go to the bill of reinforcement or bill of material. And if you select reinforcement and calculate the results, you can see that now it's not just about concrete and volume mass, etc., but now we have new part related to reinforcement, where actually you can choose two options to display the results. First is based on diameter, or here it's called cross-section. So if you select this option, you can see differentiation for individual diameters. And more simple view can be, for instance, just based on material class. So if we display the results now, you can see that here we have just material type and the total mass and total length in this area. Yeah. So now question is, because of course on the design it reinforcement level, we have just a rough assumption about amount of the reinforcement per unit volume of concrete. If you apply user reinforcement, you can have much more precise results. So question is, for instance, whether it would be useful to extend bill of reinforcement or bill of material to include not just user reinforcement, but for instance, the provider reinforcement. So let us know about this as well. Yeah? And the last topic which I would like to mention, maybe I will again display the results, that of course you can include, for instance, the price estimation, but you can also increase the reinforcement due to detailing or overlaps. So here, for instance, you can see that we have mass almost 7,000 kilograms. And now I can increase just this reinforcement, for instance, by, I don't know, 10%. And I hope, yeah, you can see that now my amount of reinforcement is increased in the bill of material. Yeah. Okay. So actually, it was last topic from today's presentation. So it's all for today. Big thanks for your attention. We are looking forward to see each other on some next webinar.